A PLC is an industrial computer and consists of a CPU, memory, inputs, outputs, and communication. The PLC will have an operating system that takes care of all the functions of the PLC, and it will have an area where we can put our programs to control the PLC and make it do what we want. The programs in the PLC consist of a large number of on and off bits that are grouped together in groups of 8 bits or 1 byte. The CPU of the PLC uses a hexadecimal code to perform functions. We humans find it difficult to program using this machine code. PLC manufacturers have made software that helps us write programs for their PLCs. The international standard IEC 611313 states that there will be 5 standard programming languages. So if a person learned a particular language on one PLC, then the basic principles should be the same for all PLCs using that type of language. There will be some features that one manufacturer will have, but another won't. The languages can be divided into 2 types: text-based, where words and codes are used to make the program; a graphical-based languages that use symbols to write the PLC program. The PLC software will convert these high-level languages into the low-level code that the PLC CPU will understand.
Instruction list is a low-level text-based language that uses mnemonic code to represent the programming functions. This is one of the original PLC languages. A program has a structure that can be divided up into 4 sections. A label is used to mark the sections of the program that can be used for program control. Instructions are the commands that the PLC program can perform. The operand is the value that the instruction affects. In this example, the value of the start is loaded and is ORed with the value of the pump, which is the latch. The result is ANDed with the stop input. The result is stored in the variable pump. Structured text is a high-level text language that is based on the C programming language. The programmer would write functions made up of a series of expressions. This language is useful for writing your own library functions that can be used in other programs. The program would be made up of labels, instructions, operands, and comments. In this example, pump equals the result of start being ORed with pump and then ANDed with. Ladder diagram is a graphical language that uses symbols to represent inputs and outputs and follows a similar layout to relay logic circuit diagrams. The 2 power rails are represented by the vertical lines on the left and right of the diagram. The diagram has rungs, which are the horizontal lines of the ladder. The inputs are on the left and the outputs are on the right. Any rung must be connected to an output, but it isn't necessary to have an input, just the connection to the left power rail. The program is executed starting at the top, completing one rung from left to right, one rung after another. When the program is connected to the PLC, you will see changes in color to the symbols depending on whether the inputs and outputs are on or off. It is possible to view the program like an electrical circuit and fault find as if you were working on a real electrical circuit. Notice how the stop button isn't a normally closed contact as shown on the electrical circuit. This will be explained in detail shortly. This is the symbol for a normally open contact. When the input variable is on, then there is a connection through the contact to the next item on the ladder of the rung. When the input is off, the label is shown in red. The contact is shown in red to show that there is no connection through the contact. When the input is on, the label is shown in green. The contact is shown in green to show that there is a connection through the contact. This is a symbol for a normally closed contact. Note the diagonal line through the contact to signify not. or negated. When the input is off, the label is shown in red. The contact inverts the signal and allows a connection through to the next item on the rung. When the input is on, the label is shown in green. The contact inverts the signal and blocks the connection through to the next item on the rung. This is the symbol for the output coil. The output coil is off when the coil is de-energized. The output is on when the coil is energized. A function block diagram is a graphical language that uses symbols to represent logic functions and other library functions. Here is a function block diagram of a start-stop circuit. The two contacts in parallel are represented by the OR gate, and the stop in series is the AND gate. Lines can be drawn between the outputs of one function to the inputs of other functions. The program is executed from the top, moving left to right down the page. The function blocks can be moved around the page and are not constrained as is with the ladder diagram and its power rails. The inputs are on the left side of the box and the outputs are on the right side of the box. The PLC program can have a vast number of library functions that can be used within the program. You will see that when you start to write programs in the PLC that you can also use function blocks within ladder diagrams. Sequential function chart is a method that allows the connection of program sections that need to be completed in a sequence or in parallel with other functions. Those program sections can be written in any of the other 4 PLC languages. When the PLC is placed in run mode, the PLC completes this cycle of operation one step at a time. First, the inputs are scanned for any changes. Those changes are then implemented into the PLC program. The PLC program is executed one step at a time. Any changes to the inputs that were detected during the input scan are incorporated into the program. If the input changes whilst the PLC is in run program mode, then it isn't acted upon until the PLC cycle returns to read the input part of the cycle. Any changes that the PLC program wants to make to the outputs are written to the outputs. The outputs are written once the PLC has completed running the program. The outputs don't change when the PLC program is running. The changes are made at the conclusion. When the outputs are being changed, the inputs are not being monitored and the program is not being run. The PLC cycle repeats and will continue as long as the PLC is in run mode. In this example, we have an assembly line that has a sensor that is counting items on the conveyor. The sensor provides an output when the items are passing, and over time production has been increasing, and now the output from the sensor is on for 0.7 seconds. The program of the PLC has been added to and now takes 1 second to run. Items on the line are being missed because the input to the PLC can be turning on and off when the PLC is running the program, and so it misses the operation of the sensor. A solution to this problem may be to put a delay on the sensor so that the output will stay on longer and so be seen by the PLC input, or make the program more efficient so that it can run faster, or to replace the PLC with a faster model.
PLCs have been around for a long time, and as technology improves, we find that practices that were okay once are no longer used. Let's have a look at a few of these obsolete practices. Back in the 80s, computer memory was expensive and came in 2 types. There was random access memory that would lose all its data when the power was switched off. Then there was read-only memory, which had to be programmed using special devices called a burner. The program was permanently installed in the device. Now PLCs use memory which is not volatile, like SD cards, that can be programmed and changed. A shift register was used to convert a word into a pulse train. It would be under the control of a clock that would step the logic 1s and 0s of the word to the output. The output could be used to control the sequence of operation of a process, and by changing the word, the process could be changed. Jump instructions allow the steps of a program to be altered depending upon the external conditions. The problem occurs when something goes wrong, and the PLC gets caught up in an endless loop and fails. Most PLCs have a timer that times how long the PLC run cycle is, stops the PLC from getting caught up in a loop. A more modern method is to use subroutines, derived function blocks, or macros.